Welcome back to Fat Mama Physics on elevator problems featuring Levi Attack on Titan. In this video, we will be doing an example and for you to give a try on one of the later examples. Here we have a question broken down to A, B, and C. I'm going to do A and B, and I'm going to give you a chance to do question C. Without further ado, let's get started. Levi has a mass of 65 kilograms, I actually searched this up, and is standing on a moving elevator. Find his apparent weight if the elevator is accelerating upwards at 10.10 meters per second squared. So let's quickly jot down what we have. We have his mass. We are trying to find his apparent weight, which we just learned is our normal force from our previous video. The elevator is accelerating upwards at 1.0, and that's our acceleration of the elevator. And that's also Levi's acceleration because he's accelerating with the elevator. Okay, and of course, the first thing I'm going to start with is a free body diagram. So here is Captain Levi. Okay, I drew him in an elevator here, and first of all, we know he has Fg, his weight, actual weight is acting on him, and there is a normal force acting on him. We know that since the elevator is accelerating upwards, his Fn must be larger than his Fg, so I'm going to draw Fn a little bit longer than his Fg. Elevator is accelerating upwards, which I will deem that to be our positive direction. Okay, so first let's start with our Fnet equals ma equation. We have Levi's mass, we have his acceleration, we can calculate for Fnet, okay? So that is possible, but what do we really want? We want his Fn. How do we find out his Fn? We know that Fnet is equal to not just your ma, but the sum of the forces is your Fn minus Fg, because Fn is in the positive direction, Fg is in the opposite direction. So if we find Fnet from this ma, we can substitute it in here to help us solve for his normal force. So let's do that first. So here I just multiply Levi's mass with the acceleration of the elevator to first solve for Fnet. Okay, we get 71.5 newtons for our Fnet, okay. So now we have Fnet, we can figure out Fg to help us figure out what Fn is. So let's do a quick Fg calculation up here, because Fg is just mass times acceleration due to gravity, which we know is 9.81 meters per second squared. And so substituting all that in here with Levi's mass, we get 637.65. Running out of room there, forgot some units. So let's first solve for the normal force, isolate it, and then we can substitute in our values. So to do that, I'm going to move Fg to the other side, and then putting in our Fnet value and our force due to gravity, substituting in here, we get 709.15, which we are going to round to 3 sig figs, giving us 709 newtons. So a little bit of conceptual understanding here. Notice this value is definitely larger than Levi's weight, of course, and that's because the bottom of the elevator has to work extra hard, not only to hold up Levi's weight, but also to accelerate him in the upwards direction. And imagine you are trying to do that. If you're trying to do that with your hand, if that's ever possible, it'll be pretty hard for you, right? So it makes sense to add these values together, giving us a larger value. Okay, so that sums up A. Now it's time to try B. So I'm going to quickly do B, and then you'll have a chance to try out C. This time, however, the elevator is ascending at 2 meters per... Wait, it's 2 meters per second. It's not 2 meters per second squared. See, this question here is very tricky. This is not telling you an acceleration, this is telling you a speed. And that means this elevator is just going at this speed, therefore it's a constant speed question. And when we have constant speed, we know the acceleration of the elevator is 0. Aha! So the elevator is not accelerating. And when we have the elevator not accelerating, we know that the forces must balance in an elevator. So let's try drawing that in the free body diagram. Somehow Levi just got skinnier, but we know that his Fg is the same, and because there is no acceleration, the force due to gravity must balance with his normal force. Okay, and because Fn is going to be Fg equal to Fg in this case, all I need to write down here is the force due to gravity, which we calculated in question A. So I'm just going to write, rounding this to 3 sig figs. The reason why it's not 2, because I never even use this number. This is just telling me the elevator is going at constant speed. It doesn't tell me acceleration. So 3 sig figs, 378. Whoops, sorry, 638 newtons is what he will feel when the elevator is not accelerating. Okay, sneaky question, right? So this is where you have to read the question carefully and read the units carefully. Okay, so this is a good time for you to pause the video, try question C, which now the elevator is instead decelerating going upwards. What does that mean? Okay, so good luck, and I will play my solutions in fast play. And here I go.
Okay, so here's the acceleration is downwards. The negative sign is to remind me, I might change it later. I have him in the elevator, which the Fg going down, Fn is smaller because acceleration is downwards. We have Fnet equals to ma, and since I've chosen a downwards direction to be positive, when I substitute in acceleration, I must use the positive value instead of the negative value, and so I kind of screwed up at the top. I just ignored what I wrote there. So putting down as a positive value, we calculate Fnet. After we have Fnet, we can use that and Fg to find Fn. So let's solve for Fn here. We get Fnet minus Fg equals minus Fn. Or if we just multiply the whole equation by -1, we can get rid of all those ugly negative signs, substituting all our values into that equation, which we have Fg minus F net, we get 585.65, rounding to 590 newtons.
All right, I went out of the page a little bit there, so sorry about that. A few things in this question I just want to just talk about. The way that I did was different than maybe before. First thing is I chose the downwards direction to be positive instead. So now my equation for Fnet looks a slightly bit different than what I did in the previous question. It's the opposite, in fact. And as a result, the equation looks a bit different when we solved for Fn. We used some values before, and we got 590 newtons rounded to 2 sig figs because 0.80 is 2 sig figs. So value is less than his actual weight, meaning that when the elevator has a downwards acceleration, he does feel lighter, okay, with a smaller normal force. So hopefully that sums up a little bit of problem-solving skills for you when tackling elevator problems. There will be one more video coming up with another example, so hopefully you'll stay tuned for that. Otherwise, thank you for joining me in on Elevator Problems Examples featuring Levi from Attack on Titan. Fat Mama Physics signing out.